Now the first step of the reaction is hydrolysis of the benzyl chloride molecule. The reactant here is benzyl chloride. It undergoes hydrolysis to form benzyl carbocation and chloride ion. That is step 1. Now the free energy of activation is the difference between the free energies of the transition state and that of the reactant, and here so much value for free energy of activation. And this is something like a hill, and if the hill is very high, let's say it is very high, then it is difficult to climb this hill, so that the reaction is difficult to occur easily. So higher the free energy of activation, higher is the difficulty or lower is the speed of the reaction. Again, bond breakage, this is a bond breakage process, and bond breakage is endothermic, energy requiring process, and the energy has to be obtained from the medium of the reaction and the surroundings if you are heating the reaction mixture or supplying a catalyst or a high pressure, etc. So from the reaction medium, the molecule has to attain the free energy of activation by a collision with other molecules, energetic molecules. That is the topic related to kinetics. Anyway, the first step of the reaction is hydrolysis of benzyl chloride, and that requires energy, and its free energy of activation is very high, and the free energy of activation is the energy difference between the transition state and the free energy of the reactant. Now the transition state for step 1 may be drawn like this, and here the resonance is avoided to avoid complexity. Then in the second step, the intermediate here is the benzyl carbocation. Now it is called intermediate because its energy is intermediate between that of the transition state and that of the reactant. So energy of the intermediate is in between, energy of the intermediate is in between that of the transition state and that of the reactant. Again, this intermediate is stabilized by resonance. Now the pi bond will be shifting like this. Now this is the pi bond and this is the sigma bond. Pi bond will be shifting like this, so that the positive charge moves over to this carbon. Then this positive charge is conjugated to this pi bond, double bond, so that this pi bond will be moving in this direction and get a positive charge at this point, and this pi bond which is conjugated to this positive charge will be moving in this direction. We get positive charge at this pi bond at this point, and this pi bond which is alternate to this positive charge will be moving in this direction, and we get positive charge over the carbon back. So these are the canonical structures, and so we can say the benzyl carbocation is stabilized by resonance, but again it is unstable because of its positive charge. Now in the second step, the hydroxide ion attacks the benzyl carbocation. Now as the hydroxide ion approaches benzyl carbocation, see the carbon here possesses a vacant orbital, and the lone pair orbital or oxygen atom overlaps with this vacant orbital, establishing bonds, and the bond formation is a gradual process like bond breakage. Initially, a long bond is formed between this positive carbon and hydroxide ion. So when the hydroxide ion forms a very weak bond, partial bond in the initial stage with positive CH2, it will be having a longer length, and the positive charge over the carbon is reduced to delta positive and the negative charge also reduced to delta negative. Now when the full positive charge is reduced to delta positive, the resonance is lost, not completely but partially lost, so that potential energy of the system increases. So this increase in potential energy shown from the intermediate is due to the decrease in the resonance possibility of the benzyl parts. The resonance of the benzyl part is decreased because the magnitude of positive charge here is getting diminished. So resonance gradually decreases, means potential energy gradually increases. But OH negative approaches CS2 to establish a bond. So the distance between OH and CS2 decreases as the reaction progresses in the forward direction. So the potential energy of the system gradually decreases with respect to the CS2 and OH, and potential energy of the system increases with respect to the C6H5CS2 system due to decreasing resonance. Initially, the decreasing resonance is important because the potential energy increases gradually. So, during the initial stages, the decrease in potential energy due to establishment of bond between OH and CS2 and shortening of the bond, the decrease in potential energy is less than the increasing potential energy due to decreasing resonance. So initially, the decrease in potential energy due to decreasing bond length or length of the bond between CS2 and OH, the decreasing potential energy between decreasing potential energy due to the decreasing length between CS2 and OH is less than the decrease in resonance or the increase in potential energy due to decrease in resonance, so that the potential energy of the system initially increases. So two things: potential energy increases due to decreasing resonance, then potential energy decreases due to decreasing bond length. Initially what happens is that the potential energy increase due to decreasing resonance is greater than the potential energy decrease due to decrease in bond length. And this continues up to the transition state, where the increase in potential energy due to decrease in resonance is equal to the decrease in potential energy due to decreasing length. Now beyond the transition state, the decrease in potential energy gains importance, and decrease in resonance is of little importance, because after the formation of the transition state, the positive charge over the CS2 group decreases to such a large extent that resonance becomes less important and decreasing bond length gains more importance, so that there is a steep decrease in the potential energy diagram. And finally, the positive charge over carbon completely neutralizes, establishing the normal bond in the OH. Now one thing here to be noted is that the transition state 1 is of higher energy than transition state 2. The peak here is higher than the peak here. So transition state 2 is having a lower energy. Why? Because in the case of the transition state 1, the bond between carbon and chlorine is getting broken. Now chlorine provides Usually an sp3 hybrid orbital belonging to the third shell. So there are 3 lone pairs over chloride. An sp3 hybrid orbital belonging to the third shell, because chlorine has got the configuration 3s2 3p5. Now the 3s level combines with the 3p orbitals of chlorine to form sp3 hybridization, so that 3 orbitals will occupy lone pairs, and these lone pair orbitals will be directed along the corners of a tetrahedron and so on. So the bond angle is 109, which is higher than the bond angle in the normal atom without hybridization. It is 90 degree in the normal atom, but it widens to 109 degree, so that the repulsion between lone pairs is minimized. Even if it is an sp3 hybrid orbital, it is longer in length, so that carbon to chlorine bond in the normal benzyl chloride molecule is longer. Whereas in carbon to oxygen bond in normal benzyl alcohol, which is the product, here the carbon to oxygen bond is shorter, because oxygen provides again sp3 hybrid orbital but belonging to the second shell. So this orbital will be shorter in length, so that carbon to oxygen bond will be shorter in length, and a short bond is stronger, so that it needs only minimum stretching in the transition state. So when the stretching is lesser in the transition state, this stretching is lesser than this stretching. So when this stretching is lesser, it has got a lower length, and lower the length, lower is the potential energy. Now this graph can be divided into 2 at the point of the intermediate, and the first half provides information regarding step 1, and the second half provides information regarding step 2. Now here the activation energy is the energy difference between transition state 2 and the energy of the intermediates, that is delta F2. Now delta F2 is very much lower than delta F1. This is a small hill, so it can be easily climbed, and so the reaction is faster in step 2. And again in step 2 the reaction is one of bond formation, whereas in step 1 the reaction is one of bond breakage. And bond formation here in step 2, it is bond formation, and bond formation is exothermic, so it is spontaneous, just like the magnets, when their fields overlap, they spontaneously move forward and come into contact. So it's a speedy reaction. So here also in step 2, the oppositely charged ions attract together, so that they speedily combine to form the product, that is benzyl alcohol. Whereas in step 1 we have to separate the atoms, and higher energy is needed, and the process is non-spontaneous, and so on. Now you consider your home is at A, point A. So you reside at point A, your home is at point A, and your school is at C. Now you walk about 8 kilometers to point B to reach your school in 2 hours. So from A to B you walk 8 kilometers in 2 hours, and at B some friend of yours pick you on his bike and reach the school within 6 minutes, and the distance is 2 kilometers. So your journey to school occurs in 2 steps. Step 1 is from A to B and walking. Step 2 is from B to C on bike. So 2 steps are there, A to B and B to C. Now speed of walking is 8 kilometers by 2 hours, that is 4 kilometers per hour. And speed of bike journey is 2 kilometers by 6 minutes, and 6 minutes is 6 by 60 hours, that is 0.1. So 2 by 0.1 is 20 kilometers per hour. 20 kilometers per hour. Now total speed of the journey from home to school is 8 plus 2 by 2 plus 6 minutes, 2 hours plus 6 minutes, that is 2 plus 0.1. 8 plus 2 by 2 plus 0.1, that is 10 by 2.1 is approximately 5. So the total speed of the journey 5 is more near to 4 than near to 20. A reaction can occur in a single step or more than one step, and the study of how a reaction occurs is called mechanism of the reaction. So from reactant to product, a reaction can occur in a single step or more than one step, and how the reaction occurs from reactant to product, the path followed by a reaction to start from reactants to products is called the mechanism of the reaction. So mechanism means how a reaction occurs. So we can reach Ernakulam from Trivandrum by train, by bus or by plane. So also a reactant can reach a product in different ways, but which path the reaction chooses to reach from reactant to product, that particular path is called the mechanism of the reaction. Now the total rate of a reaction, the overall rate of a reaction, rate here means speed of a reaction, and in chemistry instead of speed we use the term rate. Rate and speed are having the same meaning. So overall speed or rate of a reaction, here we have discussed the two-step reaction, and here the slowest step is walking, and so the total speed of the reaction or the total speed of the journey here is more nearly equal to the speed of the slowest journey step. Similarly, for a chemical reaction which occur in more than one step, the total speed or rate of the reaction is almost equal to the speed of the slowest step in the reaction. And the slowest step in the reaction is also called rate determining step. Rate determining step. And the rate determining step of a reaction is the slowest step, and when we consider the reaction of benzyl chloride with sodium hydroxide, the slowest step is the first step, which is hydrolysis of benzyl chloride giving a carbocation, because it has a higher free energy of activation, and so it is low. And the fast step is the second one, because from intermediate to transition state 2, the difference is small, so free energy of activation is small. So that this is the fast step, hence we call it the fast step. And the slowest step is the step 1, in which only one molecule is taking part, and this is also called the rate determining step of the reaction. Since only one molecule is taking part in the rate determining step, it is called a unimolecular reaction. Unimolecular means molecularity equals 1. Then the total reaction involves replacement of chlorine by OH. So when one group is replaced by another group during a chemical reaction, it is called substitution reaction. Substitution reaction. So it is unimolecular substitution reaction, and hence this reaction is termed substitution nucleophilic unimolecular, because N stands for nucleophilic. It is called nucleophilic because the reagent here is a nucleophile called OH negative. Now a nucleus is having positive charge. Philic means loving. A positive charge loving species should be a negatively charged species. So OH negative has got attraction towards positive charge due to its opposite nature. So OH negative is called nucleophile. So nucleophile here is OH negative. So this reaction involves substitution. It is unimolecular and it is nucleophilic in the sense a nucleophile is involved in the reaction, and the nucleophile is having affinity, attraction, love towards positive charge. Because nucleus is having positive charge, philic means loving, hence nucleophile is having attraction, affinity, love towards negative charge, and it should be a negative species, or it can be a species which is capable of donating electron pair. So a nucleophile can be a neutral molecule like ammonia and water. We will see later about nucleophiles. So step 1 and step 2 are involved in SN1 reaction. The free energy diagram for SN1 reaction is shown, and if we divide it into two halves at the point of the intermediate, we get the data for the first step and the data for the second step. So all SN1 reactions involve two steps, two transition states, etc. And again we understand that the slowest step during a chemical reaction is the rate determining step, and the overall rate will be almost equal to the rate of the slowest step, and rate here means speed of the reaction. Now benzyl chloride reacts by SN1 mechanism. If we take another molecule, that is tertiary butyl chloride, this molecule also reacts by SN1 mechanism. Now here the CCl bond breaks first, and that is the slowest step in the reaction. We get a tertiary butyl carbocation and chloride ion. So this step is slow, as in the case of benzyl chloride. Now we can say during the formation of the transition state, there are two stabilizing factors here. One is the plus I effect of methyl group, and the other is hyperconjugation. Now here we know the three CH bonds are alternate to the positive charge, so the CH bond can shift in this direction. These three CH bonds can shift in this direction. these three CH bonds can shift in this direction, so that the positive charge can be shared by all the hydrogen atoms. There are 9, 3 plus 3 plus 3 equal to 9 hyperconjugation canonical structures. So also the inductive effect operating in this direction can share the positive charge. Now these two effects, that is hyperconjugation and inductive effect, stabilize the molecule during the formation of the transition state. Initially during breakage the CCl bond stretches, and then during stretching potential energy increases and partial charge will be created over this carbon. This is called the alpha carbon. Now during partial charge formation, both inductive and hyperconjugation begins to operate, but the fact is that the decrease in potential energy due to slight operation of hyperconjugation and inductive effect is less than the increase in potential energy due to bond stretching. Now this goes on until a situation is reached when the hyperconjugation and the inductive effect stabilizes the partial positive charge to such an extent that the decrease in potential energy becomes equal to the increase in potential energy due to bond stretching, and that is called the transition state, as in the case of benzyl chloride. Then what happens is that the bond gets further stretched, so that the positive charge over alpha carbon increases in magnitude to such an extent, say 0.8 or 0.9 delta positive. Then there is maximum stabilization attained for the carbocationic species to be formed by hyperconjugation and inductive effect, and the potential energy decreases, and when it reaches to the t-Butyl carbocation, the stabilization is at the maximum. So a graph like the one obtained in the case of benzyl chloride is possible, where the transition state 1 will be having an approximate structure like this: Cl, delta negative, positive, CH3, delta positive of course, CH3 and CH3. So this will be TS1. Now the intermediate in this reaction will be the t-Butyl carbocation, C positive, CH3, CH3 and CH3. Now in the second step, this is step 1. In the second step, the hydroxide ion, if the reaction is conducted in sodium hydroxide medium, the hydroxide ion attacks the carbocation to get what is called t-Butyl alcohol. Now initially the carbon possesses a vacant orbital to which lone pair of oxygen is donated. Initially the bond is in a stretched condition. Then the partial charge over carbon is getting diminished, or this carbon is getting diminished, so that the extent of hyperconjugation and inductive effect gradually getting diminished, so that potential energy rises. So a rise in potential energy is obtained, and then it reaches a maximum where transition state 2 is formed, and at this point the decrease in stability or increase in potential energy due to decreasing resonance is exactly equal to the decreasing length of the carbon to OH bond, which causes a decrease in potential energy. So at transition state 2, the increase in potential energy due to decreasing hyperconjugation and plus A effect is exactly equal to the decrease in potential energy due to decreasing carbon to oxygen bonds. And then after this transition state, hyperconjugation and the inductive effect, the impact of these two effects become less important, and the bond shortening causes much larger decrease in potential energy, and so there is a steep going down of the curve and we get the product. And again the CCl bond is having a lower strength than CO bond, so the product will be having, that is t-Butanol is having a lower potential energy, than the reactant, that is t-Butyl chloride. And the energy of activation for this process is given by this value, and the energy of activation for this process is given by this value. And so we can say that the reaction step 1 is given as slow process, and step 2 as this one, it is fast and this is slow, and the overall rate of the reaction will be equal to the rate of the slowest step, and so on.